Here we are with the video for section 4.4, Lewis symbols and structures. You can see the learning objectives have been listed here for you. We have seen a little bit about Lewis symbols already, Lewis dot structures already. And if you recall, that's where we take the symbol of the element and represent its valence electrons around the symbol like this. So carbon has 4 valence electrons. It would have a Lewis dot structure like that. We don't start to pair those electrons up until we get to 5 valence electrons. Okay, so 1, 2, 3, 4, and there's 5. So first we need to be able to draw Lewis symbols for the elements on the periodic table, especially the nonmetals. We're gonna use this to determine Lewis structures of molecules. Another important part for us with regards to Lewis structures is when I draw a Lewis symbol of an atom, as I've done here, and I can see how many single electrons and how many electron pairs occur. Because often where there is a single electron, that is where we will find a covalent bond forming. So for the example of nitrogen, with 5 valence electrons, it's going to pretty easily form 3 covalent bonds and then have that lone pair of electrons as well. Now hydrogen is the exception here with only 1 valence electron. It only needs to get 2 valence electrons to fulfill its octet. So a pretty common thing that you would see happen is hydrogen and its 1 electron and nitrogen and one of its single electrons form a covalent bond like this, where those electrons are being shared back and forth. On that note, this bond now counts for 2 electrons for the nitrogen and also 2 electrons for the hydrogen. So you can see if I were to continue to add hydrogens here around this nitrogen, you can see how nitrogen's octet would then be fulfilled. It has the lone pair of electrons here, and then all of these shared pairs count for 2 electrons to both atoms in which they're bonded. As I introduced briefly in an earlier section, those bonds do not have to be to separate individual atoms because we have things like double bonds and triple bonds. So as I look at my carbon here, yes, carbon could form 4 single covalent bonds like this to fulfill its octet. And you can see I'm using hydrogen a lot here in my molecules. Those hydrogens with only 1 valence electron form bonds here pretty easily with these single electrons in other atoms. Okay, so as I mentioned a second ago, in addition to individual single bonds, we can also form double and triple bonds. I'm going to stick with our carbon, nitrogen, and hydrogen situation here. Okay, so if I wanted to bond the carbon and nitrogen together, I could form 1 single bond, but you can see here that both nitrogen and carbon have multiple single electrons. So I could go all the way up to forming a triple bond like this, and with nitrogen's lone pair of electrons, you can see it has a filled octet, and then maybe with hydrogen's other lone electron, we throw it on in a single bond like that with hydrogen. All right, let's take this a little further so you can really see how this works here. I'm going to use CO2 as an example, and I want to come up with the Lewis structure for this molecule, carbon dioxide. Okay, so the first thing I have to consider is how many valence electrons do each atom bring to this molecule. Okay, so if I think of carbon, carbon has 1 atom, and each carbon has 4 valence electrons. I'm taking this from its location on the periodic table. For oxygen, we have 2 oxygen atoms, and each oxygen brings 6 valence electrons to the molecule, so that's a total of 12. Okay, so when I begin to construct the structure of this molecule, I know I now have 16 valence electrons that I need to account for in this structure. First thing I'm going to do is connect my atoms with single bonds. Now, it's sometimes pretty clear as to what the central atom here is. So, for example, the carbon and the CO2 would be the central atom. General rule of thumb is the least electronegative atom in the molecule would be the central atom. But more often than not, you're going to have things like this where you have one atom of one type and numerous other atoms that you would bond around with. Okay, so let's connect our oxygens and carbons here in a skeletal structure. The next thing I want to do is I want to fill in lone pairs of electrons to get to my total number. And I'm going to start filling in with the terminal or outside atoms. Okay, so currently oxygen here has 2 electrons in that single covalent bond. So and altogether, my molecule with just the bonds has 4, and we said we can have 16. All right, so there's 6, 8, 10, 12, 14, 16. So maybe on my first attempt, I come up with a structure like this for CO2. Okay, now I want to see, the goal here is to fill every atom's octet. So I want to take a second and see if I've done that. And as I look at this, you can see that I have done that for the oxygen, but not for the carbon. So just to count it, each oxygen has 3 lone pairs. So there's 6 valence electrons, and then this bonded pair counts again as 2 for the oxygen and 2 for the carbon. So you can see the oxygen has a filled octet. The other oxygen on the other side would be the same. Okay, the same thing is not true for carbon. Carbon currently, with no lone pairs and all 16 of my electrons having been used up already, carbon does not have a filled octet. So at this point, what I would start to do is to change lone pairs to bonded pairs and see if that helps me to be able to fulfill the other atom's octets. Okay, so for example, if I were to take and remove that lone pair and make it a double bond here, and then remove this lone pair and make it a double bond here, have I accomplished filling every atom's octet? Well, let's take a look. If we look at this left-hand oxygen, you see I have 2, 4, 6, 8 valence electrons. If I were to look at the right side oxygen, you can see I have 2, 4, 6, 8 valence electrons. So both oxygen atoms are now satisfied with a filled octet. If I now look at the carbon, you'll see that the carbon has 2, 4, 6, 8 electrons and also has a filled octet. So every atom now has its filled octet. We just want to double check and make sure our total number of valence electrons are correct. And you'll see 2, 4, 6, 8, 10, 12, 14, 16 valence electrons in this structure. So I have the proper number of overall valence electrons, and I have fulfilled every atom's octet. So this would be a good Lewis structure. As we know, polyatomic ions are atoms that are held together by covalent bonds and then have a one charge, a singular charge. So if I had something like this polyatomic ion, CHO2 minus, my process would be the same, and I would be first determining how many valence electrons I have. Okay, now in this case, I can't forget about the charge. So my negative charge here on this ion tells me that I have an additional electron that I have to factor in. So it looks like 1 additional electron overall. Okay, so in that case, you'll see that I get 18 valence electrons. Okay, once again, I connect all my atoms with single bonds. That accounts at this point for 16 of my valence electrons. I'm going to next fill in octets with lone pairs on my terminal atoms. That always excludes hydrogen, by the way, because hydrogen is good here with the 2 electrons in the bond. So that would look like 2, 4, 6, 8, 10, 12. So now I have a total of 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. So in that regard, I'm in pretty good shape. I have the right number of valence electrons in my structure. Now comes the question of filled octets. So the hydrogen is filled with 2. You can see each oxygen has a total of 8 valence electrons, 2 in the bond, and then 3 lone pairs. Okay, so the one atom here that has not filled its octet is the carbon. So the process is to then change lone pairs into double bonds. So let's just say I take away this lone pair. Okay, and add a double bond. Have I now filled everyone's octet? The answer is yes. I still have 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. So that is a good molecular structure. And since it's a polyatomic ion with an overall charge, I'm going to finish it, the Lewis structure, by doing this. Put a bracket around the structure itself and then put the charge outside of that bracket. This Lewis structure actually brings up an interesting case, and that is the idea of resonance. And this is something covered in a later section in this chapter, but since we're here, I'll just introduce it briefly. Okay, so when I got to the point of I had added all my valence electrons and was thinking about if all my atoms had a filled octet, I decided, if you remember, to, on the top oxygen here, take one of its lone pairs and make a double bond with that carbon. There's nothing to say that when I was at this point, I couldn't have taken a lone pair of electrons from the carbon on the right and made it a double bond there. That works just the same. So the idea of resonance is the ability to take the same molecules and draw them differently in different Lewis structures. Okay, so here, if you think about this as, this is oxygen A, and this is oxygen B, you can see how those those oxygens in those 2 different structures are different. One has in one case, it has a double bond with 2 lone pairs. In another case, it has a single bond with 3 lone pairs. So this actually, to be correct here, I would need to be able to draw all potential Lewis structures for a given Lewis molecule, like, or in this case, polyatomic ion. I want to show you one other quick way that I sometimes determine Lewis structures, and I call it need minus have. And what we do is initially count or determine how many bonds we're going to have, and then put the structure together. So, for example, I'm going to go back to CO2 here. We did that math, and we determined that carbon brings 4 valence electrons, and oxygen brings 12. So that's how we did it the old way. Here I would actually think about this notion of need minus have. So how many valence electrons does an atom need versus how many does it have? How many does it bring to the molecule? Okay, so basically every atom's need is going to be 8, except of course for the hydrogen that's only 2. So carbon and oxygen are all going to need 8. And as we said over here, carbon has 4 and each oxygen has 6. So what happens here is I get 8, 16, 24 valence electrons needed in this structure, but I have a total of 16 valence electrons brought in by each atom. And I call this need minus have, need minus have. So at this point, if I take 24 minus 16, I get 8. So again, what we're trying to determine here is the number of bonds. So each bond would account for 2 electrons, right? So I'm going to take that value, 8 divided by 2, and what I've just calculated is this structure needs 4 bonds. Now as I go back and I think about connecting my atoms like this, what we did last time is we filled in everything with lone pairs and then walked it back to fill everybody's octet. What I now know is that I'm going to have 4 bonds. Okay, so currently I've drawn 2 bonds. So there's a third and there's a fourth. Now I go in and fill in valence electrons to fulfill everybody's octet. And you can see oxygen currently has 2, 4, there's 6, there's 8. Carbon has 2, 4, 6, 8 already with the 4 bonds. And the right oxygen has 2, 4, 6, 8. Okay, so now everybody has a filled octet, and then just to double check my total number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, which is what we said right here we should have. Okay, that's just another little way of doing it. It works really well for some of the smaller, more straightforward molecules that don't break any of the rules. You'll see that we have some expanded octets that break the octet rule, and so or some structures that get a little more complicated. This little shortcut to determine the bonds first doesn't necessarily work in those scenarios, but I just wanted to show you that technique as well. Okay, that's it for this section, and now it's time to just go practice drawing Lewis structures.